No, I'm not set up. I forgot to plug in the projector, sorry. I shouldn't be recording yet. I'm going to pause. All right. Oh, no, I'm not ready. I have plugged in the projector, but I haven't turned it on yet. While we're waiting for that to come on, I'll go on and start some of the announcements. There aren't too many. Is this the only class all of you are taking? You don't have any others here? Okay. If you do, tomorrow afternoon's a faculty meeting. I think the vice president said to continue classes, but in case your instructor has canceled the class because of the faculty meeting, that it is legitimate. But another issue coming up, usually on Fridays I have office hours on the Birmingham West campus from 8 to 12. I will be out of town Friday, so I will not be on the Birmingham campus 8 to 12 this coming Friday, or Bessemer campus either. Okay? And sort of a good news, bad news situation. The bad news is Monday's a holiday. There's no school. The campus is closed. The good news is it won't affect us any until we all deal with. All right, so y'all skated by on that one really well. Okay, and I just noticed that something's completely out of order here. Sorry. Yeah, no, it's fine. Okay. I can't think if there are any other announcements. Were any of you at all interested in a career in biopharma manufacturing? That's my understanding is the business of manufacturing drugs, for pharmacology. If you are at all interested in that, there is a 1-week summer program they've set up somewhere, I don't even know where, for students who are interested in pursuing that as a career. Now get this, a 1-week summer commitment. They'll pay you $1,000 to go to this 1-week thing and pay your transportation fees. So it's not a bad rate, okay? And I don't have that email anymore. I loaned it to a student to get the information off of it, and he never returned it. But if you do need the information, I can probably retrieve it. So you might want to check into that if that has any interest, or if you know of anyone who is interested in that. It sounds like a really good deal to me. Okay. I take it now of you are probably applying for a school this week or anytime soon because you're planning to come here to Lawson, right? But if you know of anyone, high school student, anyone else, this week, Monday through Friday of this week was free application week. They'll waive the application fee at many of the state schools, not all of them. UAB, I don't think was on the list. Alabama was, Auburn was, A&M, Alabama State. There were just several of them. AUM, I think South Alabama. I don't think North Alabama was, but West Alabama. Montevallo, there were just tons of them that were. You got an email stating all this, okay? And then one from Jack State and one from Alabama too that added to it. Alabama runs theirs through the 10th. Other schools end theirs on Friday, the 8th. Okay, so you might want to check into that if you know of anyone, friend, family, anyone who's wanting to apply to school. If you hit these schools, they waive the application fee for this week only. Okay, that's most of the announcements I know about. So, any questions on anything we've covered so far? All right. We are in Chapter 17, Basic Electricity, and we're in Section 17.6, which is Ohm's Law. Now, that wasn't one of the ones that was probably mentioned at the very beginning, but you can't do 17, this is 17.6. You can't do 17.7, 17.8, or 17.9, which are included unless you know Ohm's Law, so that's why we're doing this section. Now, if you recall, for ohmic materials, those are materials whose resistance matches what most materials are, linear interaction with voltages and currents. If they match that, then they follow Ohm's Law. And here's what Ohm's Law, there's several ways to state it. I'll give it to you all three ways. The first way they listed was, let me get my pen set up. Okay. I is equal to V over R. You could also write that as R is equal to V over I. And you could also write that as V is equal to IR. To me, V is equal to IR is the most reasonable, but all three of those work. Okay, what does that stand for? I is current, V is voltage or potential difference, R is resistance. Now, this only works for materials that are ohmic, but most of the materials we deal with are ohmic materials. They follow the straight line relationship. Now, the units, we went over this last time, ohms for, ohms are resistance, but I put it under current. Okay, sorry about that. Current is measured in amps. Voltage or potential difference is measured in volts. The parameter is the same letter as a unit. That's strange but true. And resistance is measured in ohms. Or you could express it this way, resistance in ohms is equal to voltage divided by current in amps, or voltage in volts is amps times resistance. So all of those are equivalent. Now, with those in mind, let's see if we can do example 1 on, sorry about this. This flash drive is a pretty shoddy little flash drive, and I haven't had a chance to go and move all the files onto a better one, so it just pops out if something touches it. So here's example 1. A heating element, and for those who came in late, I apologize for my voice, but I started getting a sore throat yesterday afternoon. In my next to the last class, that was an hour and 15 minutes, and then I had a 4.5-hour class after that, and then I've had 2 hour and 40-minute classes a day and another hour and 15-minute class, so it's going fast. A heating element on an electric range operating on 240 volts. What's that a measure of? What parameter? That's the one whose units is the same as the parameter. That's the voltage. Has a resistance. The symbol for resistance is R. Okay? Has a resistance of 30.0 ohms. Okay? The question is, what current does it draw? So we're looking for current, which is I. How would we solve for current? Which form do we use? Say again? Yeah, which one? These all are Ohm's Law, just 3 representations of it. It's that upper left. You see it? I is equal to V over R, where V is your voltage or potential difference. There's lots of ways they name it. They even sometimes call it EMF, okay? And what is that? Your voltage or potential difference. It's right there. Earth to class, come in, please. 240 volts divided by resistance is 30.0 ohms, though you're not going to use the 0.0. You can divide out 10 there, and 3 will go into 24 how many times? 8. And we can put at least 1 0 after it. 8.0, what units for current? Amps. Okay? Now, just to let you know, that's a lot of current. For instance, our computers, probably running on the milliamp, thousandths of an amp. They may be a little bit more than that, but not too much. The lights, probably fractions of an amp. 8 amps, that's a lot of current. But of course, it takes a lot of current to produce a lot of heat. And a heating element on an electric range takes a lot of heat. And they put 8.0 amps. Make sense? Any questions? All right, let's move to example 2. All right, to erase. Okay. A flashlight bulb is connected to two dry cells with an equivalent voltage, this will be your voltage, equal to 3.0 volts. Okay, same parameter, letter for the parameter as you use for the unit. It draws, and this is more typical, 15 milliamps. What's that a measure of? Milliamps is a measure of what? Amperage measures one of the three. Make a guess. Current. Current is charge per unit time. That's measured in amps. This is the symbol for current is I. Where that comes from, I have no clue. Okay? The question is, what is the resistance? So that's the unknown here. We have a little problem here. Our units. Voltages are fine in volts, but current we usually measure in amps. What does it mean to say it's a milliamp? What does the prefix milli stand for? That's, 1/1000th of an amp. So this would be, you could write it this way, 15 times 10 to the minus 3 amps. That's a sort of weird way to write it. I would just take the decimal here, move it 3 places to the left, and make that 0.015 amps. 15 milliamps, 0.015 amps. Thousandths of an amp, and that would be 15 thousandths of an amp. So what would your Ohm's law look like in this case? R is equal to V over I. And your V is? .0 volts. And you're dividing that by 0.015 amps. For Ohm's law to work and give you ohms as a result, you need to divide volts by amps. Okay, now you got dividing by decimal, which is sort of a pain in the neck. So what you do here, move that decimal back 3 places to the right, but also move this decimal 3 places to the right. And now you got 15 into 30 would be 2, right? And you got 2 more zeros before you hit your decimal, so this would be 200 ohms. And that's just a reasonable size resistance, okay? Earlier, the first problem with 30 ohm resistor, that was a, sorry, my throat's hurting so bad. That was an element that produced a lot of heat, so you had a lot of current, so the resistance really wasn't all that much compared to this, which is a 200 ohm resistor. Now, when they write it, my guess, and it's right, they'll put a bar over the first 0. Any reason why? 2 significant units there, 2 significant digits there, so you only have 2 here. That third 0 is not significant. The third digit is not significant, just that middle 0 is. All right. Make sense? All right, that was Ohm's law. Pretty quick and dirty there, but that's everything you need to know about Ohm's law. Now, they do say some stuff about electric shock, a real hazard to electricians or anybody. Nobody wants to get shocked. So it's really worth a while to probably read that. Notice here the resistance of the human body dry would normally be in the range of 100,000 to 500,000 ohms. That's a lot of resistance. But if a person is standing in a bathtub, or his or her resistance is greatly lowered by the water, any electric appliance falling into the water could deliver a sufficient current to cause death. And here's the key. A current as small as 0.070 amps, that would be 70 milliamps, can cause serious damage to the nervous system and be fatal. I don't know if y'all are old enough to remember, before they had lethal injection in Alabama, how did they execute prisoners? The electric chair. Have you ever heard of that? They call it the Big Yellow Mama or something like that. It was down in one of the prisons. And it sent a current through people, the people being executed, and that's what killed them. It does not take a lot of current to kill somebody. As little as 70 milliamps could do it. They sent a lot more, I promise you. Okay, so anyway, word to the wise, warning. That finishes 17.6. Homework exercises there would include any of the odds 1 through 13, or make it 1 to 15. 15's on the next page. Okay. Now we're moving to a new subtopic, and this is one that was included on the in the syllabus. And because in the syllabus it said you needed to have a knowledge of circuits. This is one type of circuit we call a series circuit. Now, here's basically, let me see, how they illustrate a series circuit. Okay? Simple series circuit. I've got to get up from here. They've got the tables moved so far forward I can hardly get in and out from around the desk. Okay. Plugs and everything else. Make it tough. What a series circuit is, for something to be connected in series, that's how we refer to it. What that means is if the current is leaving the battery here, which it does, it flows through every element in the circuit and flows back to the battery. That's a series circuit. Here's how we would express this in a circuit diagram. They call it a symbol diagram. Okay? The battery Sorry, my throat's going on me. You can't tell here which is positive and which is negative. One of them is, one of them isn't. It really doesn't matter. Okay? But the positive node is drawn with the long parallel line, the negative side of the shorter parallel line, and then the traditional circuit, traditional current, goes from positive to negative, and it goes through every element on the way. So this is showing the current considered to be traditional current flowing from plus side to minus side. In reality, with a series, with a direct current like this is, actually the charge is moved in the opposite direction, but it really doesn't matter because the main thing that is doing the work is the field, not the actual charges. Okay? So it doesn't matter which way you draw it, but traditionally or conventionally, this is how you do it. So it goes through the load. I'll use a slightly different symbol there for load, a squiggly line. Switch, not really all that important. You could do the same thing with just disconnecting the battery, and it goes back. So all the current flows through the entire circuit. That's what makes a series circuit. Let's see if I can get back in here without twisting my knee. All right. Now, this is quite a few slides away. So let's get out of here and go back to this one. Okay. Now, here is what we call the circuit diagram. Now, if they've drawn the battery backwards here, it doesn't really matter. I'm going to draw it the same way they did in the previous one. Plus on this side, minus on that side. Again, it doesn't really matter. The currents can go either direction. And here we hit our resistance, also called the load. And I'll draw the switch here. You don't have to have a switch here. And then the circuit goes back into the battery. That's the series circuit. This is your voltage, also sometimes called EMF or capital E. This is your resistance, the R, and the current is the flow of charge, I. So there's your three battery elements, your circuit elements. Now, let me give you their definition. An electric current circuit with only one path for the current to flow is called the series circuit. Only one path that it can go in. Okay? Now, much of the time, you can have a series circuit with multiple elements in it. Okay? I'll draw one of those. What I'll do is erase parts of this. Okay? This is a series circuit with multiple elements. This type, in fact, quite often, they'll draw the battery down here. And this one, they're indicating it's a more powerful battery, either 2 cells or something like that. Current leaving here, so the current, so this is your voltage. Okay. Now they're calling it E. You can call it either E or I. Earlier they're calling it V. Now they're calling it, V or E. Now they're calling it E. I don't know why they're inconsistent, but they are. The current is I. The voltage of the battery supplies the potential difference, which is E or I. Okay? And this shows it going through one resistor, to another resistor, and through another resistor. And then you come back and goes back to the battery. This is called R1, R2, and R3. 3 different resistors there. Okay? The current that goes through here also goes through here, also goes through there, also goes through there, through there. The current is the same current. They call it I1, I2, I3. But it's the same current. You don't lose current. You don't use current. You use the energy that the current is carrying. That's what you're using. Now, if you were to set up a voltmeter across this, you could get one voltage drop across here. You would get another voltage drop across here. You would get another voltage drop across here. Okay? One current, 3 resistors, and if you set up a voltmeter across each one, you'd register the voltage across each one. These 3 voltages have to add to give you the volts that your battery supplied. Okay? So just to give you a little bit of the way we express this, this is the voltage drop across that resistor, the voltage drop across that resistor, voltage drop across that resistor. Those 3 drops add to the voltage boost that the battery gets. Now remember what volts are? Energy per charge, joules per coulomb. That's what a volt is, joules per coulomb, the amount of energy per given charge. The current is the charge per unit time, coulombs per second. And then the resistance is you can refer to it several ways, it's the voltage divided by the current. It's the best way, Ohm's law. Okay? So that's how we refer to it. And that's why they use E here, because they use the V for the individual voltage drop, E for the voltage boost by the battery. Now, that leads to several issues. One is the total voltage in the whole circuit winds up being, from one point to another point, has to be 0. If it goes up E, down V1, down V2, down V3, winds up being 0. The sum of the voltage is 0. The current in a series circuit is the same throughout. I1 is equal to I2 is equal to I3 is equal to the current that left it. I'm so sorry. I'm going to have to go get a drink of water. Let me put this on pause and talk, but thank you for it. Okay. So a few things to note here. As I said, the current that left the battery is also the current that goes through the first resistor, and that's also the current that goes through the second resistor. It's also the current that goes through the third resistor. They're all the same. Okay? The voltage that leaves the battery, E they call it, is equal to V1 plus V2 plus V3. Now understand, the ones over on this side are the voltage drops, and the E is the voltage boost. They have to be equal numerically. Now, because of that, the total resistance of the system, if you were to place these 3 resistors with one resistor with the equivalent resistance, that would mean R would equal R1 plus R2 plus R3. Okay? Sometimes I'll call that R sub E, meaning equivalent resistor. Sometimes the book will call it total resistance. I prefer equivalent. And the book does use that title here, so let me write it down. the equivalent resistance is the single resistance goodness, this pen is doing strange things, that can replace a series and or a parallel combination. We haven't talked about that. That can replace, I'm just going to put another combination of resistors. So the equivalent resistance here is just the sum of the three. That's true for a series circuit. Now, we're going to work the problems first, the examples first, and then I'll give you the summary. That's how the book does it. Okay? Any questions before I leave this? Okay. This is making my throat feel better. Thank you. Okay. They show a figure here, and I'll try to reproduce it. Battery here. Doesn't matter how many pairs of lines you have, but battery there. Then resistor here, resistor there, just like the last one. I should have kept that. Okay. And going back to the battery. They call this R1, R2, R3, just like the last one. R1 is 7.00 ohms. R2 is 9.00 ohms. And R3 is 21.0 ohms. They say here, what is the total resistance, another way to say it, equivalent resistance of this circuit. So we're looking for what they call R. What would that be? Series circuit. What was the rule? Series circuit. Just add them together. What would that be? 21 plus 9 would be 30. 37.0 ohms. You see it? Just add the three resistors together. In a series circuit, that's what you do. Really simple. When you get to parallel circuits, it's not nearly so simple. Okay, but with a series circuit, that's it. Okay? Now, going to do some changes here, but I think when I do, it's going to mess up a lot, but let me see if I can minimize the mess up. Okay? Okay. All right, all that. All right, now we got a circuit with a resistor down here. What kind of circuit is that? Only one we talked about. Series. The same car. There's only one pathway. Only one pathway. That's the series circuit. Okay? This time it says find the current. That's the symbol I here. Find the current. You could also draw it over here. You could draw it anywhere you wanted to. It's the same current. throughout that circuit. Okay? Here your resistor 1 is a 5 ohm resistor. Resistor 2 is a 13 ohm resistor. Resistor 3 is a 12 ohm resistor. And resistor 4 down here, my goodness, R4, is a 96.0 ohm resistor. They tell us the E here is 90.0 volts. Now, I don't want you to worry about this, but I do want to say this, if I can get out. Okay? You will not see many batteries that produce 90 volts of potential difference. Your car battery is usually rated around 12 volts. Sometimes on big, heavy-duty tractors, you may see 2 car batteries together that would be 24 volts. The biggest I've ever seen was something like a bulldozer, and that had 3 basically batteries, 36 volts. I've never seen any piece of equipment that had 90 volts worth of battery. That would get so hot, that would be so much direct current, that's going to be big. So actually what they should have here is an alternating current symbol, but we haven't even done that yet. So don't worry about it. This is just figurative. It doesn't have to be a real circuit. We're going to pretend it's real, okay? Even though it's not realistic, but we'll pretend it's real, okay? Now, the question is, what is the current? It's the same current through everything there. So how do you think we're going to solve that question? Say again? Yes, let's add the resistors together to get the equivalent or total resistance, and that would be what? 5.00 plus, ohms, I forgot to put my unit, plus 13.0 ohms, plus 12.0 ohms, plus 96. Just because it's down here, it's all in the same circuit, 96.0 ohms. Now, the granddaddy and all that is the 96, but 13 and 12 is 25, plus 5 is 30, 30 plus 96 is 126, right? Ohms resistance. Correct? I'm just doing it in my head. So if y'all got calculators, correct me if I'm wrong. Is that what y'all got? Okay. So that's the effective resistance. So how do you calculate current from that? If you know the voltage and the resistance, how do you get current? Divide what into what? Okay, it's E divided by R, Ohm's law. And that would be 90.0 volts divided by 126 ohms. There, you will need a calculator. I could do some on that. I know 3 will go in both of those. 3 will go into that 30. 3 will go into that 42. And I know that 2 will go into that 15. 2 will go into that 21. So 15 divided by 21, still I need a calculator. What you get? No, 3 will go into that, won't it? Did I do something wrong? Yes, I did. No, I didn't. Anyway, what you get? 90 divided by 126. 0.714. Next digit would have been? Say again? 2. Okay, you're right to drop it. And what would be your units? Amps, perfect. 0.714 amps. And that's what they got. If you don't like the small number, you could make a bigger number, smaller unit, and make it 714 milliamps. But then that's a pretty big number, so I just assume have 0.714 amps. That's what the book used. Okay. All right, I think I'll just, rather than erasing so much, I'll just clear the whole slide. I'm sorry, should have asked if there were any questions first. Y'all are okay? Okay. This time we have this circuit. Battery or voltage source, I'm going to call it. Yes, definitely a voltage source, not a battery. They make it look like a battery, but it's not. Okay, and that goes up and goes through resistor 1, through resistor 2. It doesn't matter where you draw these things. Through resistor 3 and back to the battery. Okay, this battery, the E is 115 volts. I guarantee you that's AC. That is not DC. This is not a battery. Okay, this is a voltage supply. Okay, your current, they tell you, I, last time you had to calculate it, this time they tell you 3.00 amps. Now, frankly, that's a pretty decent current, pretty good sized current. This first resistor here is a 23.0 ohm resistor. The second resistor down here is a 14.0 ohm resistor. And the third resistor down here, they didn't tell you. And that's what the question is. Find the value of R3 in the circuit shown in this figure. This is what we're looking for. How in the world are we going to do that? Any guesses? Add what? The resistors? Actually, that's not a bad idea. We just don't know one of them. So the total resistance of the circuit, effective resistance, is 23.0 ohms plus 14.0 ohms plus R3. We don't know what R3 is. Okay? So shorten that a little bit and call it R3 plus, I think that adds to 37, doesn't it? 23 and 14 is 37. Okay, that's your effective resistance. Now, still don't have the answer. What is R3? How could we get it? What do you know about the effective resistance? It would follow whose law? If you said Ohm, you're right. I didn't think so, but yeah. Ohm's law. And how does that go? This time let's solve for R, because that has the unknown in it. How does Ohm's law go? R is equal to help me. Remember, I had three forms. The one with R on the outside would be. Now, do y'all use the triangles and circles? Do they help you any? Second? Not really, okay. What was the resistance? V over I. They're using E. Either one will work. E over I. Okay? The deal is we know both of those, don't we? So this would be 115 volts. I can't believe. Yeah. Divided by 3.00 amps. Okay. Oh, this is one way to work the problem. I'll show you another way if you want to know it later, but this is one way to work it. What does it give you? A little louder. 38.3. What units? Ohms, right? Resistance measured in ohms. Now, you see, this is also equal 38.3 ohms. That's your R, and that's equal to R3 plus 37.0 ohms. So guess what R3 would have to be? Solve for this. 1.3 ohms. They may actually say 1.30 ohms, but I don't think they should. Yeah, they just leave it 1.3. Okay, 1.3 ohms. Okay. And that's how they solved it too. Now here's the other way you could have solved it. Okay? If you remember my first diagram about the voltage drop. Whoa, goodness, I forgot my eraser was still on. Okay, let's see if we can get this back again. Where was this? Right down here. That gets uglier and uglier, doesn't it? If you remember my earlier diagram, they called this V1, this V2, and this would have been V3. But we just don't know what that is. Okay? But we know what V1 is, because from Ohm's law, we also know that V is equal to IR, right? And since the I is 3 and the R is 23, for the V1 would then be 3 times 23 is 69.0 volts. Okay, I started to put ohms. 69.0 ohms. Okay? V2 similarly would be I times R2. Well, I is still 3 amps, 3.00 amps, times 14.0 ohms, and that would be 42, right? 42.0 volts. That's your V2. Okay? Now, you add these two voltage drops together, and that gives you 111 volts. This was 115. Subtract them, and that gives you 4 volts. And then R3 is equal to 4 volts divided by 3 amps. Okay. I got my symbols all messed up. 4 volts divided by 3 amps. And that was, where did I write it? No, I wrote it, so there it is. There was my answer here, and this is 1.3 volts. So there's the other way you could do it, by individual voltage drops, and they all have to add up to 115. Okay, so there's 2 ways to work this. You might even think of another one. As long as you do all the steps right, you should get the right answer. and they got 1.3 ohms too. I put volts. I don't know where I put volts. It was ohms up there. It's ohms here. Okay. All right. The old gray cells aren't working well with this code. I'll blame it on that anyway. Now, this shows example 4 is using this answer here, and it said find the voltage drop across R3. Now, I did it the way that's the most direct, well, maybe not most direct, most correct way, but they're using this answer. Now, remember, this answer was a round off, right? It really was 1.333333333, right? But you rounded up to 1.3, which was correct rounding. But it's still a round off. So they're saying now find the voltage drop across R3. Well, you know its resistance is 1.3 ohms, or at least you think it is, 1.33333. And you multiply that, the V3 done this way would be I times R3. I is 3.00 amps multiplied by 1.3 ohms. And if you put that in there, you get 3.9 volts. Doing it the other way, you got 4. 4 is actually more correct because you didn't use round off there. But if you're anywhere that close, you're going to get full credit for it. Does that make sense? The way I did it originally, not realizing they were going to ask for that, was this one. Now, any questions? Okay. Let me leave this slide and go back to our other ones, because this is the summary slide. Now, these are the characteristics, I've said it several times, the characteristics of your series circuit. Series circuit, there's only one pathway, so there can only be one current. So your current I is equal to current through the first resistor, through the second resistor, through the third resistor, through the fourth resistor. However many you got there, it's the same current through all of them. Because it's only one pathway, you do not lose current, you don't use it up, you don't create it, it's there. Okay. The equivalent resistors of a series circuit, now don't get this confused with what later we're going to call parallel circuits. The equivalent resistance is the sum of those resistances. R1 plus R2 plus R3 plus as many as you got, that's the total resistance. And similarly, the voltage that's supplied by the battery, which they call E, is equal to the sum of the voltage drops that your resistors have. V1 plus V2 plus V3, as many as you got, those have to add. Because the voltages add, the resistances add, the current stays the same. Okay? That's the summary slide for series circuits. And that's the end of 17.7. So homework exercises here, I would do any of the odds 1 through 5, either 7 or 9. Now when they talk about EMF, that's what they mean by the capital E. Okay, 11 or 13. All right. Any questions on series circuits? Now there's another kind of circuit, and it's called a parallel circuit. Now these are the same circuits. They're just two different ways of representing them. But first let me give you a definition for what is a parallel circuit. Let me get my pen back. Okay, an electric circuit with more than one path, for the current to flow, is called a parallel circuit. Now I'm going to tell you my shorthand for this. Parallel lines are lines that don't intersect. So quite often when I say a parallel circuit, I'll say a parallel circuit. That will be how I represent a parallel circuit. I'll try not to, but that's just my shorthand. Now these three circuits, they show the switching on the switches in material, but they show it. These are identically the same circuit, just different ways of looking at it. Okay? You notice the current leaves the battery. This is your E or your capital V, whatever you want to call it. The current goes through here. There's your I. Okay? When it gets to point A here, though, some of the current goes this way and some goes this way. The current splits. Okay? It has to. Only some current goes one way, some another. It can't be the same current anymore. When it gets to this point, though, this second current here, some goes here, some goes there. It splits again. Okay? And then this current goes through this resistor. Then it teams up with this current coming through that one. And then it teams up with the sum of those through this one. And the original current goes back in. You do not use up current. Use energy from the current. Okay? Now, this is just another way to represent the same thing. It's just that here it shows some of the current going up here to R1, just like it did here. Some going to R2, which it did here, and some going to R3, which it did here. It's the same setup. These three are sort of parallel to each other. These three are parallel to each other. These are the same circuits. Okay, just different ways of expressing it. Now, I've already given you one thing that's a big difference. The currents add. In a series circuit, current's the same everywhere. Okay, here's the second big difference. The voltage here across the battery is the same as the voltage across R1, as across R2, as across R3. Same voltage across all three. Whereas in a series circuit, it was the same current through all three, but the voltages add. Here, it's the same voltage across all three with the currents adding. Same thing here. Voltage across here is the same as across here, which is the same as there or there or there. Okay? Voltages are the same. The currents add. Now, if you thought that was a little different, but makes sense. When you get to doing resistors, that really gets weird, okay? And we're going to get there shortly. In fact, maybe right now. Not yet, okay. Let me hit these. What I just said, okay, let me fill in the blanks here. Here's your I, here's your E, okay? The I that comes here, the total current leaving the battery, part of it goes here, we'll call that I1. Part of it goes here, we'll call that I2. And part of it goes here, we'll call that I3. Okay? So in a parallel circuit, I, the total current, is equal to the sum of the currents. I1 plus I2 plus I3. Okay? Parallel circuits. Whereas, if that's your E, and this is your voltage drop across R1, here's a voltage drop across R2, Here's the voltage drop across R3. Guess what? The E or V, you can call it either one you want to, is the same as V1, is the same as V2, is the same as V3. It's the same voltage drop across every element in that circuit. Okay? Very different from your series circuit. Okay. Now, again, these sort of make sense. Here's the part that gets bizarre. Okay? If you think about what is your current? Current is voltage over resistor. So that would be V1 over R1 plus V2 over R2 plus V3 over R3. But guess what? All these voltages are the same. So this could be V times 1 over R1 plus 1 over R2 plus 1 over R3. And that's equal to your current. Well, what in the world is, if you divide both sides of this by V, the V's go out here, what is I over V? Ohm's law. It's not quite Ohm's law, it's close. Ohm's law is V over I is equal to R. But this is I over V, so guess what that is? 1 over R. That leads to the third block here. When I said the resistors, strange, here's what it is. 1 over the total resistance, or effective resistance, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And then you keep on trucking as many times as you need to. Very different. The currents and voltages are different, but they're reasonable. This looks bizarre, but that's what comes out of it. No way around it. Okay? Now, they also do something here in the book they don't do on the slides. So let me go back to, y'all have this, can I erase it? Okay. Let's go back to this slide so I can write it for you. Let me get my pen back. Oh boy, my throat hurts. Okay. What if you only had 2 resistors? Okay. You have 1 over, in parallel. 1 over R is equal to 1 over R1 plus 1 over R2. You could do this with 3, R2, okay. You could do this with 3 resistors, but we're just going to do it with 2. It's so much simpler. And the more you got, the more complicated it gets. Well, if you saw something like that, how do you add 2 fractional forms? You have to get a common denominator. And what's the common denominator between R1 and R2? The product. You multiply. Okay? So here's what I'm going to do. I'm going to multiply this first one by R2 over R2. Isn't that 1? Okay. I'll multiply this one by R1 over R1. Isn't that 1? Yeah. So multiplying by 1 doesn't change anything, does it? Okay, so what do we get? This is, I'm going to reverse the order here, R1 plus R2 divided by R1 times R2. That's equal to 1 over R. But what if I wanted R? I've got to flip them. Well, I've got to flip both of them, right? So now we get R is equal to R1, R2, the product, divided by the sum. Okay. Now, I want you to give me a value for R1. Just make up a value for R1. A number. Give me a number, any number. 5, we'll call it ohms, right? Give me a resistance for R2. Make up a number. Any number. 16 or 15? I didn't hear. 15? Okay, well, let's call it 15 ohms. Okay? Now, let's plug these in. We're putting these two resistors in parallel. So let's plug in these values. That would be 5 ohms times 15 ohms. You had to give me big numbers, didn't you? Divided by 5 ohms plus 15 ohms. Okay? Well, 5 times 15, if I'm not mistaken, is 75 ohms. Y'all can check my math. Oh, that's actually ohms squared, which is strange. Okay. Divided by 20 ohms. When you add those two together, well, this ohm will cancel one of those out, so you're back down to ohms again. And this would be something like 75 divided by 20 would be 3.25, I think. You check my math. Ohms. Did y'all check my math? You gonna trust me? Okay, y'all are, I've got some swampland I'll show you. No, okay. Now, here's the interesting thing there about this. Notice we started with 5 ohms here, connected it in parallel with 15 ohms. And what's the effective resistance of that circuit? Less than either one of them. What? You put 2 resistors in the same circuit and the total resistance comes out smaller? Yes, it does. That's what happens with parallel circuits. Resistors add as inverses, so it's an inverse relationship. The total resistance goes down when the individual resistances go up. Now, that may feel like it doesn't make any sense, but I bet you sometime or another you've either had this happen to you or you've heard of it happen. I'll give you the example of the first house that my wife and I rented when we moved here to Birmingham. We hadn't really built up enough cash to think about buying yet, so we were renting there. She had been renting, I'd been renting where we lived before, so we rented that first year. It was an old house, a leaky old house, but it was a pretty old house in south side of Birmingham. And hard to keep warm, but fortunately I think the landlord paid the utility bill, so that was okay. She lived next door. But we were trying to be reasonable and stuff. But it was an old house, like I said. Every room, I think, originally had just one electrical plug. It was an old house. But they had renovated the kitchen. And the kitchen had several plugs on it. Okay? So, all right. Now, the main circuit breaker, the circuit box, didn't have circuit breakers. It had the old fuses. Have y'all ever had to mess with them? Okay. You may have run into this before too. So they had renovated the kitchen. So to me, that meant they rewired the kitchen. Well, what they did, they just put extra circuits in the kitchen. They didn't rewire the whole place. And what would happen if you had the microwave on and then the refrigerator compressor kicked in, the microwave would go, and when the compressor kicked in, the microwave would go, and then pop. everything would go out. Okay? And here's why. When you added one resistance to another resistance, your effective resistance went down, your current went up, and the current went to the fuse. For a while there, I thought we were, now this was how long ago it was. Any of you remember Big B? Yes. You do? Okay. Big B was the old, just about the only drug chain in Birmingham. Now we've got CVS, we've got Rite Aid, we've got all these others. But back then, the main, and not the only one, that was when the only grocery store in town was Bruno's. Okay? Except they had Food World and Food Giant or Food Line or something. But they were all owned by Bruno's. Okay? So it didn't matter. They were all Bruno's pretty much. Well, there was a drugstore, Big B, within walking distance of where we lived. So I made that path many a time to go buy more fuses. And we get a box of fuses, and in a short time, there we go. So we had to start planning things. Wait till the refrigerator cuts off, then plug it through the microwave. But don't do your coffee until you fit, It was, you had to do that. Because the more you put on the circuit, the less the resistance for increasing the current, blowing the fuses. And it was frustrating. Nowadays they have circuit breakers, which are much better than fuse boxes. Okay. All right. Good deal. Thank you. I don't think we'll be ready for it tonight. It'll probably be next week. All right. Can you wait a week? Sure. All right. Good. Good. I want to make sure I wasn't upsetting you too badly there. Okay. All right. Now, they have a comparison of parallel circuits. They say consider a water system. So that's where we're going to go back to our the book slides. Okay. Here is the next slide that they have in the book. Now this is over on the top of page 474 in the book, but the points they're making are at the bottom of page 473, so you have to flick back and forth. But they're saying here, just consider the pump. Remember when we did the pump analogy, water pump analogy? That's equivalent to the battery or your voltage supply, your EMF, whatever you want to call it. The current is the water flowing through the pipes. The current is the charges running through the circuit. Okay? Pretty good analogy. Okay? Here we have, you break it into three different pathways, three different pipes that you go through. Okay? Now, if your pump's running along here, pumping water, if all you had was one pipe here, small pipe here, it could only pump the water that that pipe could hold. Okay? But if you added a second one, then it could pump more water. Added a third one, you could pump even more water. Because you get more and more pathways here. So the resistance to the flow of water actually goes down the more you add the pipes. Even though each one of these pipes has a certain resistance. But if you have more of them, there's more way for the water to flow. That's the same thing that's happening here. The effective resistance of the whole system here is less than the individual resistance of the individual pipes. So that's what they're getting at. So here are the 3 points. The total amount of water flowing through R1 plus R2 plus R3, that's the total water flowing through the system. Okay? Just like the current, I1 plus I2 plus I3 is the total current flowing through the system. Okay? The water flowing past point A divides into three branches. That's what we said before. I1, I2, I3. So these three add to be that I. It's exactly what we said here. I coming in here as I, breaks in I1 plus I2 plus I3. The larger pipes have less opposition to water flow. This has less resistance than that one. This has less resistance than that one. That's the greatest resistance. But it doesn't matter. The big pipe handles all of it. The big pipe has less resistance than any of the resistances there. So that's why the resistance of the circuit, the overall resistance, goes down when you add more smaller resistors. Okay? I think we beat that to death, didn't we? All right. So the same thing here on this side. This is on the next page. The total amount of current flowing through the circuit, I, coming out of the battery, going back to the battery, is the sum of I1 plus I2 plus I3. Okay? The current flowing past point A here divides into three currents, I1 plus I2 plus I3. They almost said the same thing. The smaller resistances have less opposition to current flow and therefore carry larger currents. They didn't give the sizes here, but if this was a smaller resistor than these two, more current's going to flow through it. If this is the greatest resistance, less current is going to flow through it. You can't see that with the resistors here, you can with the pipes there. So, let's do example 1, bottom of page 474. Okay. Well, let's see. I don't think it was the next slide. No. Whew. All right, example 1. Sorry. Okay, sorry about that. Find the equivalent resistance of the circuit shown in this figure here. Here, let me get my battery back. No, my pen back, sorry. I don't even know what I'm typing. Here's my battery. Okay. Goes up here and then goes down through R1. Goes over here to R2. Oops, they're supposed to connect there. And this goes over here to R3. Okay. R1, R2, and R3. R1 is 7 ohms. R2 is 5. Goodness, my throat hurts. R3 is 12.0 ohms. Now, I don't know if you remember this far back, but if you go back to example 1 in the series circuit 1, you'll see these are the same sizes of resistors. They're not quite. The third one was 21, this one's 12. Okay, they were close, but wrong digits. Okay. It says find the equivalent resistance of this circuit. In other words, we don't care, we don't know what the battery size is, we don't know what the current is, we just want the equivalent resistance. What's the formula for parallel resistors? Remember, that's the reciprocal relationship. 1 over R is equal 1 over R1. Continue.
1 over R2.
Continue. Plus 1 over R3. That's your equivalent resistance. Now, I'm going to plug in the numbers for you. 1 over 7, now I'm not going to put the point zero zeros, plus 1 over 9, plus 1 over 12. Now, the reason I'm doing this, I'm going to tell you. Now, do both of you have calculators or a phone or something like that? Mm-hmm. Okay. I'm going to show you the easy way to do reciprocals. Okay? Now, let's start with this. You press the number 7, and then you find a key that either looks like this. 1 over x or x to the minus 1. See if you can find a key that looks like either one of those. 1 over x or x to the minus 1. Or maybe some other way.
You give your decimal.
See there, 1 over x. Okay, yeah. Well, wait, yeah, don't, yeah. It will give you a decimal. You found the Okay. All right, so you do 7 reciprocal key, I'm just going to call that reciprocal key, plus 9 reciprocal key, plus 12 reciprocal key, equal, now that gives you 1 over r. The answer is 1 over r. So to get r, hit the reciprocal key again. What do you get?
2.964.
Okay, you get the equivalent resistors, R equals 2.924. Is that what you said?
964.
964. Okay, we only need 3 significant digits, so let's round that to 2.96. 1, 2, 3, look to the right, 4 is less than 5, and that would be ohms. Now, what did we say before? The equivalent resistance is less than any one of the other 3. Or 4, however many you got. And sure enough, this is looks smaller than any one of those. See, that is a reasonable answer. It may not make sense to you, but that is the reasonable answer. Let's see how the book did. Look at that. 2.96 ohms. Now, they show you that same stuff over here at the top of page 475. Now, their symbol is x to the minus 1. I said either one of them. So I think both of your calculators or phones had 1 over x, right? Mm-hmm. So same difference. Okay. And you see they got 2.967964705, blah, 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 blah. Only use the first 3 digits. Unless that 4th digit is greater than 5, then you bump it up by 1. Does that make sense? All right. Now, we have another circuit that's really just like this one. So I'm going to just erase the pieces that I don't need. Okay? The formula is the same. The numbers are going to change to protect the guilty. Okay? I won't take these out. I'll change those, and this answer probably won't be the same. Okay, even though it looks a little different, this is the same circuit as the one in your book on page 475. Find the total current this time, that's I, of the circuit shown here, and this is R1 is equal to 23.0 ohms. R2 is 14.0 ohms. And R3 is 5.00 ohms. With the E here of 90.0 volts. Now, I know we had one before with the 90 volts. How close is this to that one? $90, and we had 5, 13, and 12. No, these are different. The 5 is the same, but the other 3 aren't. It doesn't matter. man. Okay. It says find the total current. We're looking for I. Now again, there's two ways to do this problem. You can do it either way you want to, whichever way you see best. What's the way that you would suggest doing it?
The way we just recently did.
Say that again.
The way we just recently.
Okay, the one up at the top?
Yes, sir.
Okay. So what would you have?
1 over 23.
23 plus 1 over 14 plus 1 over 5. Okay, y'all are good at this, so I'll let you figure out what your R is.
0.31.
Oh, look at you, huh?
0.31. If I round it, it'd be 5.
315,
Yes, sir.
and that would be ohms. Okay, now what are you going to do with that? That wasn't what they were asking for. They were asking for current. How does current relate to resistance and voltage? I need her back there to say, whose law? Ohm's law. And how does that go if you're looking for current? I is equal to V over I or E over I. Doesn't matter which one you call it. No, not I, R, right? I couldn't hear what you said and I wrote down the wrong thing. Okay. And you got your V or your E. That's 90.0 volts. Your effective resistance was only 0.315. Now, frankly, if you still have that on your computer screen or calculator screen or phone screen, just do 90 divided by the number you got there. This is ohms. And what would be your current? A huge current, isn't it? 280. Oh, no, they say 28.6. Wait a minute.
Well, it says if you multiply 90 divided.
Wait, let's back up. I think wait one. They got 3.18, not 0.315. Let's go back and check our numbers again. 1 over 23 or 23 reciprocal. Oh, I think you forgot to reciprocate the last one.
I did.
That's it. So let's go back and punch it in real quickly. I thought that seemed like an awfully small current. Resistance. Okay. 23 inverse plus 14 inverse plus 5 inverse equal, and then do the inverse.
3.176.
Okay, so that would round to 3.18 ohms. But if you leave that in your calculator, that won't hurt. Okay? Well, maybe it would be hard to do. So just do 3.18 and do 90 divided by 3.18 ohms. That would be something on the order of 28.3. What unit? Amps. Very good, because current is measured in amps. That's what the book got. Now, remember, there was another way to do this. And if you like this better, especially if you didn't like all those reciprocals and forgetting to do the last reciprocal, you could do it this way. You could do this one. 90 divided by 23. Punch that in. Plus 90 divided by 14. Plus 90 divided by 5. Equal
28.3.
28.3. So you see what you did. You calculated the current across this one, current across this one, current. You added the three currents together, and you got that. Now, frankly, that's almost as easy as doing all that.
Yeah, it is easy.
And you're less likely to forget that last reciprocal. Okay. So that's another way to do it. So do it however makes the most sense to you. Okay? 28.3. All right. Let's see if we can get example 3 done. Ooh. Ah, you've already done it. It said find the current through R2 in this figure. How did you get the current through R2? Oops. You did 90 divided by 14. And what did you get?
6.43.
90.0 volts divided by 14.0 ohms. And what did you say it came out to?
6.43.
6.43. What units? Amps. Very good. Let's see how they did. .43 amps. Good for them. Good for them. All right. All right. I'm going to keep the figure and change my numbers. All right, sorry this is taking so long. I may be old, but I'm slow. All right. This time, we have a voltage of 115 volts. We have our first resistor of 38 ohms. We have our next resistor of 49 ohms, and we don't know the resistor in R3. But we do know the current here, and this current, the total current is 7.00 amps. That's a fair amount of current, okay? What it asks for first is the equivalent resistance, which usually we've been calling R. I like to call it REQ, so I know what R I'm talking about, equivalent resistance. So what would that be? How could we get that? And by the way, not knowing R3, we can't use the formula at the top. We may use it later, but we can't use it now. How would you get the equivalent resistance of that circuit? Hint, you know the voltage and the current. Yes. Whose law? Ohm's law. How does that go? Say again. Okay, not I. We're looking for R. So R V over I. Okay, and we know both of those. Your V is your E here, 115 volts divided by your current, 7.00 amps. So what's your effective resistance of that whole circuit? A little louder. I still can't hear. 16.4. Is that what you said? Okay. What unit? Ohms. Right. Okay. And that's what the book got to. Good for them. Okay. Now the second thing said, find the value of R3 in the circuit. Okay. That's going to take some mental gymnastics. Okay. That's going to take the formula we have up here, and we need to solve it for R3. Okay. Now, again, there's a couple ways to do it. I think the easy way is the way I'm going to show you. Let's first solve it for 1 over R3. So what we'll do is 1 over R3 is equal to 1 over R minus 1 over R1 minus 1 over R2. You see what we've done? You subtracted these two from that one, leaving you that one. Does that make sense? Yeah. So that's what we got. Now, with your handy dandy calculator and knowing how to do this, let's plug in the numbers. I'm sorry, I should have done that. This is equal to, I'll do it down here, 1 over R3 is equal to 1 over 16.4 ohms minus 1 over 38 ohms minus 1 over 49 ohms. Same as before, except this time you're not adding, you're subtracting. A little louder.
70.2.
70.2 ohms. Okay, that's a pretty large number, but that could be. I think you did hit the reciprocal key the last time, otherwise it wouldn't have been that big. Oh, look at that. That's what they got to. Good for them. That was a big old resistor at the end. Okay? Now, you might say, is there another way to get this one? I bet so. This, to me, is a little longer, though. And I think you got that one down pretty well. You could use this divided by this to give you that current. That divided by this to give you that current. And those two currents together, subtract from that, and then use that I3, which you just got, multiplied by E to give you that. That's a lot more calculation, so I think the way you did it is probably the best. But there's always, usually more than one way to skin a cat if you don't like cats. But I don't know. We won't go into that. Okay. Now, that was example, which one was that? That was example 4. Oh, and they showed you over here how to do that and how you got it. Yeah, they said 16.4 reciprocal minus 38 reciprocal minus 49 reciprocal equal. You get an answer and then reciprocate that too, and that's what you get. So let's see if they have a slide. Can I erase this or y'all need it a little longer? Okay. here is our summary slide for the parallel circuits. Characteristics of the parallel circuits. Remember, we did one like this. In a parallel circuit, the currents add, because you have to split and go each direction. So the currents add. The resistances add by the reciprocals to give you the reciprocal of the effective resistance. But the voltages are the same across everything, because there are many paths where the voltages are the same across each. In a series circuit, the currents are the same for all of them. Resistance is just regularly add, not reciprocal, and the voltages add. Okay. Now, where are we now in the text? Oh, we finished 17.8. So, homework exercises here. There are not many of them, just 2 odd problems, 1 and 3. But they each have 4 parts. So, no, one has 4 and 3 has 2. 3 has 3 parts. So, do 1 and 3. And what do you say we pick up compound circuits next time? Okay with that? All right. Now, as soon as we finish compound circuits, I think that finishes all we're supposed to cover in chapter 17. Yeah. We're not doing electric instruments and voltage sources and that kind of stuff. So we just got that one little section to do, but it is sort of involved. So we'll do that, and I'll have this test for chapter 17 ready for you next time. Then we'll move right into chapter 18. Okay? 18 is magnetism, and we're just covering a couple of sections in 18. A few sections. I said a couple. It'll be more than that. 1, 2, and 7. And because that's so short, we're going to go into 19 and do 3 and 5. And that's going to take us basically to the end of the term. Now, it seems like we're a long way from there, but if you think about it, we've got next Wednesday, the following Wednesday, then you have Thanksgiving. Then we have one more Wednesday, and then final exam. I think that's right. So really, we're going to be ending just about right, I think. We may not even quite get through with things we need in 19, but we'll try to get as much as we can.
Do you know exactly what day our final exam will be?
Your final exam will be your last test, and I'll give it to you after that last class, and you return it to me that next Wednesday.
So is it December 11th?
Probably. I haven't looked at the calendar.
Great. I have a question about that.
Yeah.
Graduation is the 13th, and I'm scheduled to graduate.
Right.
So will I have to bring that back to you before graduation?
Okay. Well, okay.
Do my final grades have to be in before graduation or no?
Well, if you bring it in on the 11th, I'll have time to get it in by the 13th. So it's not a problem, I don't think. Is it? Whoops. Isn't that what you said? The final exam is due on Wednesday the 11th.
Well, I don't know if you're giving it to us on Wednesday the 11th.
No. I give it to you the last day of class, which was the previous Wednesday.
Okay, that's fine.
And then you turn it in the next week.
So the last day of class is the Wednesday after Thanksgiving?
I think that's right.
Okay.
Yeah. Because Thanksgiving is very late this term. It's this year. It's the latest it can be. It's on the 28th. If it was on the, if it was, you see, the month of November started on a Friday. So the fourth Thursday is the 28th. That's the latest it can be. We come back for 1 week. That's when, at the end of that class, I'll give you your test. And then the next week you bring it back.
Okay.
And that's all we've got to do then. Now, what we might be able to do is have pizza or something if you wanted to do that. But if you, I don't know, it's up to you. We'll talk about that later.
Yes, sir.
Okay. Is that going to be okay?
Yes, sir.
Okay. I think that'll work out pretty nicely. Because the fall graduation, they're not nearly as picky about getting grades in as early as they do winter and spring, the spring graduation.
Okay.
Yeah, so, but I'll still have them in on time. If you have your testing me on Wednesday, I can get them graded.
Okay.
And in the system before Friday. And I don't think you have anything to worry about.
Okay.
All right, good deal. Any other questions? Good question, by the way. Yes.
About the internship you were telling us.
About what?
The internship for class.
Right, about the pharmaceutical. Yeah. Okay. Are you said you're not taking any other classes here, are you? Okay. Let me see if I can find that. I'm going to go and shut this down. Well, let's see. I don't usually do this, but I'm going to do it this time. Okay. I'm going to open my email and see if I can find that email that Dr. Wilson sent. Okay. Sorry. This is such a sorry system. Okay. Now, I can't remember if I deleted it or not. I'm going to first check my delete files and see if it's there. Deleted items. Yep, there it is. There's the website. So you want me to just forward this to you?
Yeah.
Or you want to just copy it?
You can just send it to me.
Okay. You'll need to give me your, ooh, come back here.
Does it say on there like
What?
when the application is due and stuff?
Not in the email, but if you go to the link, I think you can get it there. I haven't gone for it. Okay. I'm going to forward it. And you want to type in yours or you want me to?
Yeah, you can.
Okay. What is it?
Emily.
Say again.
E-M.
E-M.
I-L-Y.
Oh, your name. Okay. Oh, there you are.
Mm-hmm.
Your Lawson email address?
Mm-hmm.
Okay. So, yeah. I didn't know you were in my system. Okay. So send it to you. Okay. And then if you go to the link, you should be able to find out all the information.
Okay, thank you.
All right. Glad to. Glad you're interested.
Well, it's not for me. I have a friend.
Oh, I see.
He wants to be like a pharmacist.
Oh, I see.
Yes, I think that would be a good opportunity for him.
Yeah, they're paying like $1,000 to go. Now, is he also a student or not?
He's at UAB.
Is he? Oh, he's a student at UAB? Hey, that's where it came from, so good deal. Well, not the thing. The woman who sent it to Dr. Wilson was from UAB.
Okay.
She was at microbiology though, so
Thank
yeah.
you.
Glad to. Have a good week. We'll see you next week.